Hi, everyone. My name is Travis Rector, and I'm a professor of physics and astronomy at the University of Alaska Anchorage, and I'm also one of the organizers for a group called Astronomers for Planet Earth. And this session, we are very pleased to have Dr. Marshall Shepard with us. This is the Q&A session based upon the talk that he gave. And so first off, if you're watching the recording of this and you haven't seen Dr. Shepard's talk, there is a link to it below, which I highly encourage you to watch before watching the Q&A. And the purpose of this talk is just to give everyone who has had a chance to watch the video to talk with Dr. Shepard and ask questions. So I'll very briefly introduce Dr. Shepard. We only have a half hour, so I can't go over all of the achievements and accolades that Dr. Shepard has, but I will mention that he is a professor at the University of Georgia. He is the distinguished chair of the Georgia Athletic Association Distinguished Chair, which I wanted to ask you about that. That's a very interesting title. He is also former president of the American Meteorological Society and is the director of the Atmospheric Sciences program. And he also spent 12 years at NASA-Goddard. Dr. Shepard, thank you for joining us today.
Sure.
So
I'll answer that one question because I get it often.
Sure. Yes.
So the Georgia Athletic Association Distinguished Professorship is just an endowed chair position at the university, in the same way that you might have the IBM Professor of Computer Science or the Coca-Cola Professor of Business. Our athletic association gives millions of dollars to the university. It's a separate entity, and there are a couple of very high-level endowed professorships competitive for some of the more, active and successful faculty. So I just happen to have that. It just happens. It has nothing to do with athletics other than they give me money.
Okay, interesting. Fantastic. Okay, well, I'm going to go ahead and take the pleasure of asking the first question of you. Your talk, of course, was about the connection between climate change and the weather. And I saw recently a quote which really resonated with me and made me think of your talk, and that is that weather is the new polar bear, that it's becoming sort of the face of climate change, and is where people are hearing more about the weather. And the question I have for you is based upon an experience I had recently where when we had, of course, the big blizzards happening on the East Coast, which is occurring more and more frequently recently. As an Alaskan, I'm resentful whenever other places get more snow than we get. And there was, snow in Central Park. And I was talking to someone and they said, well, it seems like climate change is responsible for everything. And, we talk about the connection between climate change and blizzards and drought and flooding. Do you have an answer for that? Do you have a way to help people, other than by going a deep dive into the science and explaining how each of these events is connected? I sense a little bit of fatigue, maybe that.
Yeah, I think that's right. I think it's real. I mean, I think because I even cringe sometimes when I see, climate change is related to that worm going in at 5 p.m. today in its hole. I think there is a little of that actually. And so I'm very cognizant of that fatigue. But the reality is, every single weather event happened within the context of a changing climate system. And so an atmosphere that's a bit different from the same atmosphere 100 years ago. And, weather is so connected to agricultural productivity, it's connected to health, infrastructure, and so forth. So it's not a stretch to say that climate, it's interesting. I just dealt with this a little bit myself this week. I wrote as many of you know, I write an article. I'm a senior contributor to Forbes Magazine, and I wrote an article this week. I've been watching the Olympics, and I guess Michaela Schifrin has one of our top skiers in the slalom has not been doing that well. And so I wrote an article sort of suggesting that perhaps and I deliberately entitled it the way to be a little bit provocative, is climate change sabotaging some of our top downhill skiers? And the point I was making is that because many of the places now that are having the Winter Olympics are in places where they're having to generate sort of man-made snow, from listening to many of the experts, they say that snow is the sort of artificially generated snow gets icier in certain conditions, and it's a bit more difficult for some of the slalom skiers, at least, to manage. And so, I had someone, oh, so you're blaming her poor performance on climate change. I was like, now, if you read the article, I actually made the point that much of the drought there and snow drought in that region is related to sort of more climate variability and sort of seasonal scales than climate change. But the reality is there are studies that suggest that by the end of the century, only Sapporo will be suitable to host the Winter Olympics in its current form under the highest emission scenarios. So I think that fatigue is real, but I think it's actually technically a correct statement if you really look at many of the things that it's actually mentioned in that context.
Interesting. Well, I have plenty of questions, and I don't want to hog all the time. So if anyone else here would like to ask questions, feel free to raise your hand, and we will call on you.
Yeah, I'll raise my hand. Yeah, I wanted to follow on that because Travis was asking about the difference between climate and weather, and that's what your talk is about. Because you hear people saying, well, how can we predict climate change? And no one can predict the weather, but they don't seem to understand the difference between climate and weather. And one definition of climate I heard was that it's an average of the weather conditions over the past 30 years. But I've heard of other definitions of climate involving averaging over large spatial areas. Can you give us like the simplest possible distinction between weather and climate that we can hang on to?
Okay, I'll give you two examples. I'll say weather is your mood and climate is your personality. I'll start with that. You probably heard me say that before. But I actually don't like the definition of climate in terms of averages. Weather to me, climate is actually the statistics of the weather. It's not just the average. It's the max min, it's the frequency, it's the distribution. So it's really the statistical, spatial and temporal representation of the statistics of weather. That's really how I describe it, because it's average, but it's also the top sort of 1 percentile hurricane intensities, and it's also the top 10 percentile cloud cover. So it's really the sort of descriptive statistics and beyond, and so that's really how I convey it. And so it comes into play because oftentimes people that skew a little skeptical on climate change, like, oh, you all changed the name from global warming to climate change. So I know what you're up to, but in reality, as given the era of COVID that we're in, I explained that global warming is just one symptom of the broader climate change, in the same way that a fever is one symptom of COVID or one symptom. So I've always been a little uncomfortable. Global warming is one aspect of climate change, but stronger hurricanes is also one aspect of climate change, and sea level rise and reduced snowpack and earlier onset of spring. So there are various manifestations that sort of really are tied up in your question.
Yeah, another expression I've heard is that climate is what we expect and weather is what we get.
Yeah, no, I can give you all kinds of those. The one that I like is weather is what you're wearing today, climate is your closet. So, right. Because you dress for today's weather, but within your closet, you probably have clothing for different types of things that could happen, whether it be rain boots or overcoat or shorts or so forth. Another one that I often see or hear is, weather is a baseball player's at bat, whereas climate is his overall statistics. So,
I like that. Gabriel, you have your hand up. Why don't you go ahead?
Yeah, thanks. Lower my hand. So I was wondering about this plot that you showed in your talk about the attribution and our ability to attribute certain events to climate. And so you said that it's maybe I'm going to pronounce this wrong, but tornadic storms and the extratropical cyclones that were least able to kind of correlate with climate. What are the research gaps there, if it's really kind of the physical attributes that we're not clear on?
That's a great question, actually. So we heard quite a bit of that recently in December when we had those tornadoes that came through the Mid-South, parts of Kentucky and Illinois. So there was all of this media, oh, climate change caused those tornadoes because we're not supposed to get tornadoes in December. Actually, we do get tornadoes here in December. They're not as common, but they certainly aren't uncommon. We actually get tornadoes in every single month of the year. So I was in that talk, I was referencing a National Academy's report that I served as a co-author on attribution. And the way we framed that National Academy study is we use something called 3 legs of the stool. And those 3 legs of the stool are physical understanding, length of the data record, and can we produce the event in the climate models? And so events that sort of ranked high on each of those 3 legs had greater attributable confidence, if you will. So tornadic storms, one of the most difficult things right off the bat is the climate model resolutions are too coarse to represent those convective storms that will spin out a tornado. So we can't even really see them, quote unquote, in the climate models. And so that's one reason they fall lower on the scale. Secondly, much of what we know about the observational record of tornadoes has come in the Doppler radar era. And so there's a Doppler radar bias. So if you look at tornadoes, there's an uptick in the number of tornadoes, but that's mainly related to the fact that we detect them better because of Doppler radar. And so, that's one of the things. Now, the physical understanding side of that 3-legged stool, there is physical understanding that there are some things that we know that likely would lead to more intense convective storms that would produce tornadoes. But that's just one leg of the stool. It didn't outweigh those other 2. So that's why we had low confidence. Now, that report was published in 2016. Since that report, there have been new studies that have come out by Victor Gensini of Northern Illinois, who's one of the top scholars in that area, and Harold Brooks at the National Severe Storms Lab, that suggests that the environments that are conducive to the production of tornadoes will likely increase over time. Now, you notice I said the environment, still didn't say that would lead to more tornadoes, but probabilistically thinking, you would expect that if the environments will be more conducive, that would lead to. So that's why we just have to be a little bit careful when we talk about sort of the tornadic or severe convective storm connection to climate change. One thing that is interesting, and I think it is related to climate change, although we don't really know the reasons why, what we all learned about is the traditional quote unquote tornado alley. And by the way, I hate the term tornado alley because it actually gives people the presumption that that's the only place that tornadoes happen. But we do know that the activity, the occurrence of tornadoes has shifted more from sort of the Great Plains more into the southeastern US. And that may be related to some shifts in the axis of the jet stream and so forth that could be related to overall sort of Arctic amplification processes, which you all certainly are familiar with. Arctic amplification is sort of more intense or more rapid warming in the Arctic regions or the polar regions, which in turn loosens the gradient in temperature between the poles and the tropics, which in turn causes for a more wavy or saggy or jet stream pattern. The example I give in more public talks is if you're playing tug of war and you've got 2 sides pulling on the rope, you've got a really taut rope. But if one side loosens their grip, the rope sags some. And so when we're talking about a relaxed gradient between the poles and the tropics, you're sagging the rope, if you will. You get wavy or jet stream patterns, which mean more intense extremes in the overall sense.
Interesting. Well, you answered 2 of the questions I had for you, so thank you for that.
Okay.
Adrian, go ahead. You have your hand up.
Great, thanks. Yeah, I have many questions also, and I also just want to say I really appreciate your analogies and the 3 M's and the personality versus your mood, and these are extremely helpful. I so agree and appreciate someone who can come up with these, because not everyone is as good as some people at doing it. So I really appreciate your sharing those. And that connects to my question, which is, one of the things you said in your talk was about, creating end-to-end scientists, and I thought that was very well put. And then there's a question of how, what are the things that we should change in how we educate, our, upcoming students who are, in the pipeline, and re-educate ourselves who've already been in the fields for a long time. And I'd be really interested to know, what actions you're taking and what ideas you have about that.
Well, if I could have answered that question more specifically had NSF funded a recent proposal, because we actually were trying to get one of these, I guess I forget what they're called now, this is one of these big training grants. I forget what they're called anyhow. But yeah, the concept of end-to-end science is very important. And I think, fundamentally how we were all trained as graduate students, we were trained to be scientists that publish in the literature and present at conferences and follow the scientific method and ask questions
and do the reverse pyramid that you were talking
right,
about. Absolutely.
Exactly. But we were not trained with the tools to invert the pyramid. And so, for example, in my own department here at the University of Georgia, instead of just having graduate seminars where we have a speaker come in and give a scholarly topic, we have seminars on media training, and we have seminars on how to effectively use social media and so forth. So I think we have to fundamentally sort of rethink the sort of graduate seminar, if you will, for students. I think we have to incentivize early career. So here's one of the problems with the current tenure system, for example. Some of the most innovative and creative science on a campus is being done by assistant professors. And you want to share that with the media and with policymakers and in blogs and so forth, but they're de-incentivized to engage in those types of activities, because we know the way to get tenure is publish or perish and get grants for the most part. So we have to incentivize the system to encourage other metrics of productivity. I'm at a point in my career where, I'm still near the top in my department in grants every year and papers published, but I looked at my H index the other day, and I guess it's pretty high. And I looked at the number of citations that I've had, and I think it's pretty high. And I think it was like 10,000 or something. I've had 15 million people read my Forbes articles. And so I'm reaching far more people with Forbes than with people reading my papers, which are, fairly well read from a scholarly standpoint. But I just think we need to, change the model of how we're professionally developing graduate students with some of the suggestions I mentioned, but systematically incentivize our graduate students and young early career professionals to engage beyond the ivory tower. I think those are two, and some of those one of those is a really big ship, because to turn and the tenure process and fundamentally giving more weight to someone that engages with a policymaker or is willing to go on CNN or so forth. And then the third thing that I would add is we have to engage in social media. There are studies that show that most of the American public or the broader global public consume science information in social media. And if we're not there as the experts, then people with misinformation are glad to fill that gap. So.
Well, we'll get to you in a second, but I'd like to ask a follow-up question, which is related. It seems like one of the biggest challenges we have, and this isn't unique to astronomers, I think this is true of scientists in general and just people in academia. I think one of the biggest challenges is getting astronomers willing to engage in advocacy. There is this culture of the ivory tower that, as you say, our focus should be on publishing in the journals that only we read. What do you say to a scientist who says, I don't feel comfortable working in that space?
Well, I agree on the advocacy part. I don't believe we should be advocates. And so what I mean by that is there are a lot of really important climate advocacy groups like the Citizen Climate Lobby and others that I support wholeheartedly what they do, but I won't engage with them or join or be active, because I think if I'm seen as a climate activist, it sort of weakens the credibility of my published science or my objectivity when I go testify on Congress. So I actually do believe that there should be a line blurred between scientists and activism. One of my former colleagues at NASA-Goddard Space Flight Center is Jim Hansen, who's, many people know, is sort of one of the godfathers or founding notions of the modern climate change movement. But, I disagree with some things that Jim did later in his career, like chaining himself to the fences of coal mines and things like that, because for all the good science that he does, people will just see him as an activist, and they may say his science is cooked or biased because he's such an activist. Now, having said that, engaging in the public media or with policy or testifying before Congress or the state house in Alaska, that's not advocacy. That's taking our science to people who need that information and making sure that they understand the clearest and best science out there and let them make decisions based on the science. So there's an art to finding the fine line between advocacy and activism versus conveying the science in a way that's usable by practitioners and decision makers.
Okay, thank you. William, you want to go ahead?
Yeah, I wanted to amplify what you're saying. If someone says that scientists should speak to the public, I would say scientists owe it to the public because the research is publicly funded. So
they fund us for the most part. But
Yeah.
we've had this sort of, there was this idea that popularizers, scientists who speak to the public aren't serious scientists. One of the things that I've really, in the latter part of my last 10 years of my career, have really tried to, really shatter this myth that they're mutually exclusive. You can be a really good scientist and publish and get grants, but still be effective in the media and on CNN and on the Weather Channel. And I was fortunate enough to be elected to the National Academy of Engineering and the National Academy of Sciences last year. And in my citations, it spoke to my contributions in my science, but also my contributions in redefining what a public scientist is. I was particularly proud of that. But go ahead, William. I didn't want to.
Yeah, I wanted to ask you. I mean, we were talking about attribution a short time ago, and I wanted to mention, well, I live in Vancouver, in British Columbia, which is Canada's westernmost province. And from about mid last year onward, there have been a number of extremes of weather. From June to August of 2021, for example, there was no rain. There was the heat dome. Then after that, a couple months later, widespread flooding after, basically drought and then flooding. And
were you
now,
getting some of the atmospheric rivers up that way?
That's right, exactly. Yeah. And in January, a record cold temperatures, temperature minus 10 C, which is like 12 Fahrenheit or something like that, which is unusual for here. Even in the wintertime, it's usually not, below freezing. Now, climate attribution studies could not account for the heat dome, which lasted only a week, but it was like, I've lived in Texas, so I know how hot it can be, but it was having that temperature here where there's air conditioning is not as widespread is really difficult to take. And climate studies, apparently, climate models could not explain the heat dome without also including the 1.1 degree Celsius global warming from the industrial beginning of industrialization. But even with that, it was supposedly just a 1 in 1,000 year event. So I'm wondering if there's another heat dome soon, then you got to question that. So my question is basically, is there something important being missed by the climate models?
Yeah, I think the climate models are really good now. I mean, they have all the sort of spheres of our system, the biosphere, the cryosphere, the atmosphere, the hydrosphere, the oceans, and so forth. I think the real challenge is, I think we still don't necessarily, I gotta be careful. The climate models can still do better with three things from my lens: representing aerosols, representing clouds, and the grid size. And some of these things, because remember, the radiative feedbacks associated with clouds is very important to sort of amplifying some of these heat events. So one of the big uncertainties in the climate science community is we know, because of the Clausius-Clapeyron relationship, which is a very sort of fundamental physics relationship linking temperature to the capacity for water vapor in the atmosphere. So we know that because of that, we likely are going to have more clouds in our atmosphere going forward as climate continues to warm. But the question of the day is, will they be more high clouds or will they be lower, thicker clouds? So in other words, will we have lower, thicker clouds or higher, thin cirrus? And that the question of that determines whether we end up with a positive or a negative feedback in the system. Because if we get higher, thinner clouds, they sort of radiatively amplify the greenhouse effect. Whereas if we get a more lower, thicker clouds, they actually serve to block the incoming solar radiation or insolation. And so I think those are things that can create some problems with the climate model assessing these heat events as well. But then just sort of resolution, the climate model resolutions are still fairly coarse, relatively speaking. And so if we're looking at a region, say around Vancouver down to Seattle, there could be some localized microclimate effects, subsidence and around topographic relief and so forth that are sort of adding to the heat that the models are just not resolving to. So I think those three things are things that I have my eye on. And then of course, ultimately, just for a longer term, getting the scenarios right. I mean, you often do see the RCP, the pathway 8.5 scenario given, which is the worst case scenario, and for good reason, because we're somewhat on that path. But do we have that scenario right? Do we have the land cover change in the models correct? Those are still open questions.
And then what about the deep ocean? Does deep ocean, does that affect?
Yeah, I think that, one of the things that Michael Mann has been talking a lot about is this thermohaline circulation. And that was really the premise of the movie The Day After Tomorrow. If you saw that movie, you got this thermohaline circulation that kind of goes around the planet, sort of dives down places really deep up in near Greenland and goes down deep and comes back up. And one of the things that I always tell my students at University of Georgia is the Earth is always trying to put itself on a heat diet. And that's because most of the heat that it receives is in the tropics, and there's not as much heat in the polar region. So ocean currents, hurricanes, weather are always trying to redistribute that heat out of the midsection poleward. And so we know that some of the changes in the ice region, the melting in Greenland and some of the ice sheets, is introducing more fresh water into the ocean system, and that disrupts the thermohaline circulation. So yeah, we have to understand those dynamics as well.
All right, thanks.
Thank you. I want to be respectful of Dr. Shepard's time.
I've got about 4 or 5 more minutes. I'm good. I definitely want to get to Chris and Gabrielle.
Okay, Gabriella, you had your hand up first, so we'll go to you, and then we'll wrap up with Chris's question.
Yeah, thanks. I'm really fascinated by clouds and all of the uncertainties that they add to climate models. And I was wondering what you think would help us kind of address this challenge. Do we need more, data collection? Is it really kind of the microphysics of cloud formation itself? Like, how do we get to better accuracy in terms of cloud modeling and understanding?
Well, 2 things. One, I think we need a continued generation of observations of clouds. So NASA's CloudSat mission, for example, is a very important mission because we need a long enough record of that type of cloud observation so that we can, because the CloudSat mission and some of the other satellite-based missions that we have now in orbit can tell us about the population of clouds, their altitude, and so forth. But we need a long enough record to then assess whether we're seeing more high clouds, low clouds, mid clouds, and so forth. So I think we have the right observations now. We just need a long enough record. So that's critical. But then the other thing is, one of my colleagues at the University of Georgia, Dr. Gabe Cooperman, is working on something called superparameterization. This is a generation of climate models that on each grid point of the climate model, there's a cloud resolving model. So we have cloud resolving models that can get at the convective scale of a thunderstorm or a cloud. Right now, in many of the climate models, because they're so coarse, we use something called parameterization. We just say, okay, relative humidity is greater than 85%, there's probably a cloud there. But it's over a resolution of 50 kilometers or 10 kilometers. We need to resolve those clouds at the individual scales that they're happening, because they release latent heat as the condensation process is occurring. And so those latent heat releases are what's driving some of the atmospheric dynamics in part. And so I say long-term climate observation, cloud observations, and cloud resolving models embedded within the climate models.
Thank you. Chris, do you want to go ahead?
Sure. Yeah. Well, clouds are made of water, so that actually ties into my question, which is water vapor. So, when I teach about global warming, greenhouse effect in my intro astronomy class, I mentioned that water is a greenhouse gas, but I don't play it up very much because I just assume that if we have too much water vapor in the atmosphere, it'll precipitate out and it won't just keep going up. But what I learned in your talk is that as the globe warms, the capability of the atmosphere to retain water increases. So, and that's a positive feedback loop, or actually, what's the term? Vicious cycle, I think is what I should be saying. So how much of a factor is that? And is that something we should be talking about also?
Yeah, I mean, the remnants of Hurricane Ida moved over into New York, and there were 3 inches of rainfall that fell in Central Park in an hour.
Wow.
that's consistent with the peer review literature that suggests that the top 1 to 3% intensity rain events is very different in 2022 than they were in 1950. And that's because of this additional capacity of water vapor in the atmosphere. So even when people say, oh, blizzards might be more intensified because of global warming, that's counterintuitive to people. But the fact that our mean atmosphere is warmer means there's a greater capacity through this Clausius-Clapeyron relationship. That's the physical relationship that describes what I talked about at the top. So I just dropped into the chat an article that I wrote in Forbes, because occasionally I'll get people that say, well, why do you always focus on carbon dioxide when when water vapor is a greenhouse gas as well? Mm-hmm. And so this article that I just dropped in the chat, I wrote it back in 2016, I think, talks about why, and I think I mentioned this in the talk, the greenhouse gases are they're the apples in the climate apple pie. In other words, there are a lot of ingredients in a climate system, water vapor, changing solar insolation and so forth, but the greenhouse gases are the dominant forcing. And so I talk about that. But yeah, the reason we're getting more intense rainstorms is that you've got essentially more water vapor for those storms to tap into once they form. And so you're getting more intense rainstorms. And here, and I don't know if you're dealing with that as much where you are, but here in the contiguous US, places like where I live here in the Atlanta area, we're getting more flooding as well. And that's because of a triple whammy. You have more intense rainstorms because of what we were just talking about. You've got more impervious surface, so there's less infiltration into the soil and more rapid runoff into the streams and lakes and rivers. And then you have a stormwater management system in cities that were engineered for 1950s and 1970s rainstorms. So they're being overwhelmed. So.
Yeah. Okay, thanks. And does that extra water vapor in the atmosphere capture as much infrared emissions from the Earth as the CO2 that's in the atmosphere?
Well, that's what I kind of deal with in that article. So
okay, all right, I'll check it out. Yeah, thank you.
Yep.
Okay, well, it's been a half an hour and I want to be respectful of your time. Thank you so much, Dr. Shepherd, for taking the time to meet with us. I really appreciate that you fit us into your schedule. I know all the things that you do. It must be hard to even find hours to sleep in the night. I do want to mention before we go that Dr. Shepherd has two amazing things that I recommend everyone to check out. The first is his show on the Weather Channel called Weather Geeks, and also
it's a podcast now.
Sorry, podcast, yeah. And also that he writes for Forbes Magazine. And I don't know how you do it because you post several times a week.
Yeah,
interesting stories about what's going on, and I find it a very useful go-to resource after there's a major weather event. If you'd like to know more about the science connecting that event to climate change, he's the first place I go to check that out. So I highly recommend that to everyone. And as they say on the internet, we will put links to those resources in the comments below.
Yeah, and feel free to follow me on. I was going to say, feel free to follow me at Dr. Shepherd 2013 on Twitter, because that's where I usually post a lot of those articles. So,
okay, I'm not a Twitter person, but if you are, please do follow Dr. Shepherd on there as well. So, thank you again. This has been fantastic, and thank you all for coming today. And thanks again to Dr. Shepherd. This has been great.
Thanks, everyone. Bye-bye.
So helpful. Thank you so much.
Yep. Thank you.
Bye, everyone, and we'll see you next time.
If you're interested in Astronomers for Planet Earth, you can learn more at our website, astronomersforplanet.earth, and on social media as well. If you would like to be notified about future talks and events, please follow and join us.